Hello, my name is Colin Doyle, and I'm a Senior Consulting Engineer at Juniper Networks. Welcome to the fourth video in my updated Apstra and EVE-NG Lab series. In the last video, we onboarded our virtual nodes for DCA and DCB. We actually first started by creating some custom device profiles, a step that is not necessarily required. Go watch the video to find out why we did it. But we did create those, and we onboarded the switches. So the state that you should be in right now is all 12 switches should be here. They should have the vjunos-lab device profile that we defined, and they should be in a ready state, acknowledged with the off-box agent installed. If you're in that state, you're ready to go. And if you're not, jump over to the Elevate community for the previous video, and let's figure out why. In this video, we're going to be building our blueprint, which is just Apstra language for a fabric. Because we're abstracting the complexity of that fabric build, we don't need to come to this process with a big Excel spreadsheet that's got IP addresses and ASNs assigned to each node. We just need to give Apstra access to pools of information that it can then use to construct the fabric. And then if we need to represent that information outside of the system, we'll just pull it out and there's your spreadsheet. So let the tool do it for you. Once those pools are defined, we will create the connective tissue between the device profiles, which represent the physical hardware, and the logical representation of those devices in Apstra, called logical devices. Oh, real tricky, huh? And the connective tissue is something called an interface map. And we talked a little bit about that in the last video. In fact, I thought that step was in the last video until I realized I had reached the end of my instructions. Once we have that connective tissue built, we will define the logical relationship between those devices. In this case, since it's a fabric, the leaves and the spines. And with that information, we will build a template that will be used to deploy a three-stage CLO fabric. Let's get started. Where we're going to go first is those resource pools. You'll note that there's some predefined. You also note that we support 4-byte ASNs. Out of scope of this discussion, you can use these default values. There's no reason you can't. I think most folks are probably going to come into this process wanting to define their own information. I figured I would do the same. We're going to use 65100 through 65199 for DCA. All these ranges are going to have way more resources than we'll ever use. But I want to make sure that I'm getting hopefully close to what folks are going to do in a production data center, which is obviously going to be a much higher scale than what I have here. So those two are created. Now we'll go over to our IP pools. You'll see we support IPv6 if you were quick there. Out of scope here as well. And I do love IPv6, so it is difficult for me to say that. But I needed to draw a line somewhere so that this video that is already at 272 slides worth of content that I'll share in 11 videos long, and my best guess didn't get longer. We're going to create 5 IP pools here. There's some defaults again you could use. But I think most folks, even though they're not going to have the big Excel spreadsheet, they're going to have blocks of IPs that they're going to want to implement. We're going to have loopbacks for DCA, so the 192.168.1.0/24. We'll create a second here. We'll have loopbacks for DCB, 192.168.2.0/24. We will have fabric links. Obviously, you can't just get away with loopbacks. You need to have interface IP addresses as well. Oh, fabric. Fabric, this will be 10.1.0.0/16. Yeah, again, not going to get even close to touching all those addresses. 10.2.0.0/16. Oh, hang on. That needs to go here. This would be DCB. Fabric. I love it. Fabric. And then one final one. This will be for external links that will be shared between the two fabrics in the form of the external DCI peering, 10.3.0.0/16 create. Fantastic. All right, so I talked a little bit about how logical devices are the abstraction of devices in your fabric, and we use interface maps to marry those to the device profiles, which is the physical representation. It's abstraction, again, very important if you have a tool that is multi-vendor. We will be defining a pair of logical devices for vJunos. We'll also do a pair of logical devices for vEvo. Even though we're not using it, again, I want to represent these workflows for folks that might want to deploy Evo in their environment. We'll go to resources here and logical devices. Obviously, there's a ton here already, and I'll talk about what these default AOS ones are. These are usually used for generic systems. We'll create a new logical device. The first one will be vJunos-10x1. In this case, I'm using that to represent the fact that this has 10 interfaces of 1 gig dash spine. We're going to create a logical device for the spine role, and we're going to create a logical device for the leaf role. You can see that we have that connected to down here. Remember, it says connected to. If this is a spine, what's it connected to? Well, it's connected to leaves. So don't think, oh, I'm building the spine, I should check spine. No, don't do that. That's not what we do. So we got spine. It's a leaf device. We know that vJunos we built that has 10 ports. And let's see here. We know that they are operating at 1 gig. So we want to get all that set. Then we click this button that says create port group. Boop. And it takes us to this screen. And all those look good. So we click, well, we'll click create another because we have another one to create. This one is going to be for the leaf role, the vJunos-10x1. These are all using the same device profile. If you've got in your physical environment different spines and leaves, that's pretty common. You would have, you could represent this differently. You could give it any name you wanted, honestly. This, I think it's just handy for me to include the device profile I'm using, or at least nod to it, and then the type of interfaces, and then the role in the name. You're not going to deal with this much after you build the fabric, put it that way. So again, we've got 10 ports. Because this is a leaf, it will connect to spines and it will connect to generic system, which is just coded language for anything that exists outside the fabric. That could be an external router. Outside the fabric, it could be a host. This would be where your servers connect. But that's what generic means. These are, again, 1 gig interfaces. We click this button to create the port group. Everything looks okay. And then we say create another. Now you can skip this step if you don't want to build anything for vEvo. This is what it would look like, 12x100. We have 12 ports of 100 in our device profile. Spine, move this up 12 ports. These are 100 gig. And since this is a spine, we know it connects to leaves and nothing else. And we'll say create port group. And then we've got one more. And that is vEvo-12x100-leaf. 12 ports, 100 gig. We know since it's a leaf, it's going to connect to a spine in a generic system, create that port group, and then create will take us out of the workflow. If you want to double check your work, you can type the letter V here, and you'll see, frankly, none of the other default ones start with the letter V. So we'll see the ones we just created, and we want to make sure that where we see the word spine, it says leaf here, and where we see the word leaf here, it says spine and generic. This is very important. I've messed this up before, misreading my own notes, and gone to build the racks and realized that I couldn't put devices where I wanted to put devices. Great. Now we're going to go to interface maps, design, interface maps. And you can see this is somewhat iterative. You start here and you work your way down until you get to templates, and that's where you create your blueprint. So we move to interface maps, and we'll create a few of these. And again, this is the connective tissue between the device profile and the logical device. And you can see it's pretty straightforward if you ever forget that, and it's all right here. Don't go straight to name. If we pick our logical device and you just type in vJunos, we'll start with the spine because that's the order of my instructions over here. And then we select a device profile, vJunos lab. It will auto-populate the name. Just do that. It's easy. We need to click this, expand this menu, and we need to click 0 and highlight all the way to 9 so that they're all active. Here's the number we're looking for right there. Great. We need to verify these are all checked, and then we click create another because we're going to do one for the leaf as well. All right. Again, skip the name, vJunos leaf, device profile, vJunos lab. Select interfaces, Check to make sure that's all 10s. These are all check boxes. And we'll do our v-evo ones as well. Exact same process. Wash, rinse, repeat. Here we do v-evo. We'll select the spine and v-junos evo lab. Interface, highlight all, check boxes, create another, and we'll do the leaf, and we're done with this part. V-evo leaf. Junos Evo Lab, select 1212, all checkboxes, and create. Done and done. And we can double check that by typing in V and apply. And there's a couple more because the letter V is in a few of these. I think if we go to the last one, we'll at least see the V-Junos Lab. There might be a better way to search here, but we can definitely see the ones we've created. They stand out pretty well. Terrific. The next step is defining some racks. And this is where we take these logical devices that we've just created and we configure the logical relationship between them that will then form the foundation for the template that becomes the fabric. We go to rack types here. You can see a couple defaults. Again, we're going to create our own. And this is also kind of a fun place in this video series because this is the first time we have a workflow we're encountering that is different from the workflow in previous versions of Apstra, including the last video series that I did. If you look at the screen, you will see that we have create in designer or create in builder. The designer workflow is a new workflow where a sort of workspace is created and you can create these representations of the switches. It kind of looks like a diagram. The builder workflow is exactly the same as the workflow that's existed in previous versions of Apstra. I'm going to use the legacy original workflow builder for Data Center A, and I will use the designer workflow for Data Center B. Now let's start by saying create and builder, and this will be our Data Center A workflow. For reference, we're at slide 13 of 54 in my instructions right now. So that's when I said this video is going to be longer. I wasn't kidding. Call this border rack DC-A. And this is an L3 CLO. We need a leaf called switch. Logical leaf device is v-junos 10x1 leaf. Great. And this is running ESI lag. And you'll note that when I say none, my border rack, and border rack is where I'm going to connect devices outside of the fabric facing the core. There's only one. When I say ESI, now I have two. I don't know a lot of people that are going to run a single switch at the board, at any leaf, whether it's the border or server. So you want to click that ESI so that you get two devices. Now we can just click create. We'll just say create another. And now we're going to build a server rack, and this one's going to be a little bit more involved. Server rack DC-A. This is an NLBL. You can define these. You might ask yourself as we get in, like, what if I connect more servers, which will be under this generic systems field. You can always do that after you've built. This is just sort of a baseline. The rack types give you an opportunity to build kind of these elevation diagram representations within the Apstra tool. So if you have identical or similar rack configurations that iterate throughout a data center, you don't have to design each one specifically. Similar first couple steps here. Leaf name, we'll just call it switch. We do that, it creates a unique name here. So we're just saying what the device is. The logical leaf device, again, is a v-junos leaf. And links per spine. Let's keep scrolling through here. This is ESI, so we can see that we have a pair. And the spines don't come into play until we get to the templates. So if you're wondering where that is, we just haven't gotten there yet. We're going to now switch to generic systems. There's going to be three. Obviously, we've got three hosts that we're testing with. These, like I mentioned in the last video, are going to be represented in the fabric as what we would call generic systems. We'll obviously give them names that match the names that they have here. but anything that sits outside the fabric is a generic system. So I will, unless it's like an access leaf or like another switch that is a different type of design that's out of the scope of this discussion. So we have a generic system. We start by clicking the first button, and it says generic system group. We'll call this the name of that generic system, A-BMS-1. That's the same name it has in our topology. The logical device we're using now, and I mentioned these before, these pre-built interface maps. It says EOS, and that's because since it's a generic system, we need Apstra to know how many ports it has, but it doesn't really map to a device that's in the fabric, and it doesn't need to. We just need to tell Apstra how many ports we're connecting from the fabric to that device. And because these are all 1 gig interfaces, and because they're going to be using ESI lag, we're going to be using the 2 by 1 gig interface map. There it is. You can see it's just like 2 ports of 1 gig. That's all that means. So this is a generic device that will connect with 2 ports of 1 gig. You'll see that we use a different one for this single homed bare metal server. That'll be, guess what? EOS 1x1. Terrific. So that's done. We need to add a logical link for that. That logical link is a name that we're going to associate with the lag we're going to use. And this is actually where we tell it to use ESI lag. We're using switch that auto-populates, dual homed, and you'll see what this looks like up here. As we build this out, you'll see these diagram start to build out as well. We're going to tell it to use lag P active, and then we're going to verify the link speed, and we are going to click down here to add the next bare metal server. Boop. So it'll be, move my instructions along here, A-BMS-2 and EOS-2x1-1 and logical link name A-switch-lag2 dual homed lag P, and one more generic system, and this is the single home device, and that is A-BMS-3. Logical device in this case is EOS 1x1 because we have 1 port of 1 gig. Add our logical link. That is A-switch-1. We're going to put the word lag in there because there's no word. We're not using lag. We'll say the name is, oh, I didn't mean to put that there. I put it in the wrong place. A-switch-1 here. It is single homed, and we need to decide which switch, whether it's the first switch or the second switch. If you're curious, that's up here, switch 1, switch 2. You can obviously see that this is connected to switch 1. So we'll make sure that that just verify that is on single, oh, all the way down, no lag, switch 1. Perfect. So verify that that looks the way we expect it to. This should roughly match your diagram. See? And click create. Actually, I don't think I'm building the VEVO ones here. DCB. All right, so we're going to use our designer workflow for the other data center, DCB. Everything that we just did, we're going to do here. You'll just see that the work stream's a little different in this environment, but it's exactly the same except we have one less bare metal server. That single home bare metal server does not exist in DCB. Rack DC-B. Let's start by creating a leaf. So click the leaf button here. Click the gear. Label it switch like we did in the other workflow. Our logical device, same as the other one, Junos leaf. And we're using ESI lag. We do need to click this right here because we are going to have links to a spine device. So we should tell it that we're doing that. It's funny, in the other work stream, this is a 1 by default. Here we actually have to change it to 1. Now we can click create. Oh, oh wait, because that's the border rack, of course. I was thinking it was the border leaf for a moment there. And I'm like, wait, we should do more. But no, it's just the border rack. There's actually, we don't have to worry about the generic systems that are the servers that we're defining. I know I mentioned that there are generic systems that are configured for external routers. We'll define those, and they are still called generic systems, which is called external generic systems. We'll define those in the blueprint after we've deployed everything. So it is still, we're still using the terminology. We're just not doing it here in this work stream. Again, to reinforce that you don't have to have this exact. We do know that networks change and evolve and scale. So you're not in a box here. This is just your initial configuration for deployment. Click the leaf button, click the gear, change this to switch, change this to vJunos leaf, click on the links per spine, say 1, switch this to ESI lag. You can see that we now have 2 of those. That's great. And now we need to click on this to create a generic system. And this is where we define our bare metal servers. So we've got the first one in our topology named B-BMS-1. It's using a logical device. Like we said before, it's going to be an EOS logical device, 2x1. If you're building this data center with vEvo, obviously use 2x100-1 would be the one that you would use. Actually, you can see it right here. Because all the ports that are on that leaf are 100 gig, you would have to define the logical device for your generic system as 100 gig as well. Just so you know, within the Eve topology, it's fine. It'll be gig on the other side. None of the virtual machines care about the actual speed. It's just EOS will care, because if you try to say, oh, I'm going to connect this switch that's only 100 gig ports to a generic system that's only 1 gig ports, it will complain. So that's just a note that's relevant if you're using vEvo, that will differ from the workflow that we're using here. And what I'm going to do here is a little interesting. I'm going to click this and I'm going to draw a box around these. And I want to show you that this here is what we need to click next, but I can't click it until I've highlighted everything. If I highlight some of it, it doesn't work. But if I highlight all of it, then I can click this button to actually define the links that go between all of these devices. It is just 1 link per. So all I need to do here is just click create, and you'll see that these links are already there. And then I need to give this a name like I did with the other one. It will be switch-lag1. I have a count of 1 link per, first and second. Lag P, everything should look okay. Let's create the other generic system. Move that to a place where it's not overlapping with the last one. B-BMS-2, logical device, again, EOS-2x1-1, because it's 1 gig interfaces. This one, if I try to draw a box, I'll cover everything. On my keyboard, which you can't see, I'm going to hold my Alt button, and I'm just going to click each of these while holding the Alt button, and you'll see I'll highlight the ones that I need. Then I can go click this link. Click create, change the name to what you want it to be, B-switch-lag2, verify the rest of this information, and I believe, because I haven't scrolled my instructions for a while, that we're done. If we look at this, that looks a lot like this. Perfect. Click create. Oh, what did I get wrong here? Border rack B, display value. What? Okay, what did I get wrong? Border rack. Oh, it's because it's called server rack. Thank you. There we are. I wonder how many of you saw that when I first typed it and have been yelling at the screen for the last 10 minutes. Okay, we're kind of in the home stretch. We're beyond the midway point at this point. We're going to create a template, which is going to take those rack types and connect them to spines. We're going to have 1 template for each data center. So this first one is DC-A. It's rack-based. It is a unique ASN, and it is multi-protocol BGP. Scroll down a bit, we'll add in the topology, which is going to be mixing our rack types together. We're going to have border rack DCA. We're going to have server rack, all the way here at the bottom, DCA. And we're going to use our logical device. We're defining this for the spines. If you noticed in the other workflows we were using for the rack types, the only logical devices we saw were the leaf devices. This is, again, like I said, where we define the spines, and we have 2 spines. Boop. And how many? Count links to super spines. We don't have spines, so that should do. Let's show the links. That all looks correct. Create another And the next one will be for DCB, rack-based, unique, MVPN. Click that add rack the first time here. DCB border rack, DCB server rack, spine logical device, regionalized Evo spine. Obviously, if you're using Evo, use the Evo information here. We've got 2 of them. This all looks okay. Click create. There is our DCB template. Now we're going to create our blueprints. Click on the home button. Say create and deploy blueprint, or just click on this button over here and say create blueprint. Either way. DC-A. We're using a data center reference design. We're not going to talk about freeform in this video. That is a very deep well that will come, maybe never, actually, if I got to do the service chaining for the firewalls. It's interesting. It's just, it's a whole other thing. I talk about in other videos. So there's our DCA. You'll note that it's not, oh, I forgot to, I didn't forget, actually. I just created a new one, and it's already complaining, even though it hasn't given me a chance to do anything yet. DCB, that's it. Looks good. Create. Done. All right. So now we have DCA and DCB. And you'll note that there are going to be build errors. And that is because I have created this scaffolding for the blueprint, but I have not assigned any of the resources or assigned any of the devices to it yet. So we're going to click stage, and we're going to see a heck of a lot of red, which is great because the red tells us where we need to focus our attention. I'll click first on, just kind of note, I'm going to start using this terminology where I'll say staged physical topology. I'll make an effort to walk you through when we're going through the menu here. I would also encourage folks to go over to the Elevate community following the link in the description and download the companion documentation. First, we need to assign ASNs to our spine, and you'll never guess it's the ASN pool that we created for DCA. Great, click save, move to the next one. And as we move through this, you'll see red turning to green, assuming you don't accidentally click the X button. We'll go here, DCA loopbacks. Now you know why I named things the way I named them, because I wanted to keep them as intuitive as possible. Loopback IPs for leafs, also DCA loopback. Don't forget that there's this little arrow over here. If you don't see in your pool, there are 2 pages. That was a beginner's trap for me when I first started using Apstra. I'm like, where'd the pools go? It's not here. No, it's there. You just weren't looking. And then we have a DCA fabric. Save. Great. Moving from left to right, we now go here for interface maps. For our spine, click this. Pretty straightforward. Only one option, update assignments. And then for our leaf, I use this, I check here, and I can say leaf and say assigned and save myself some clicking. You can do that for the spines as well. Any chance I get to show you both ways, I will. And we can ignore this for now because there's no interface maps associated with our external devices because there doesn't need to be. Go to devices, and here's where we actually connect up our physical hardware and associate it with the blueprint. You'll see these system IDs. It's somewhat out of, somewhat out of sequence of how I have it represented here. You'll note that I go 11 through 16, border, border, spine, spine, leaf, leaf, which means that when I'm going spine, spine, server, server, border, border, it goes 13, 14, 11. Actually, pardon me. Is that right? Because it's border, border. So hang on here. You got to get this right or things will be really silly. 15, 16 for the border. And then the server rack. Oh, this is 11, 12. Ha, I almost made the mistake I was warning you against. So border, border. And hey, look at this. These are out of sequence. And these are out of sequence. Let me flip this over. Spine 2, spine 1. All right, so just get this right. Okay, so and spine 2 is 14. Spine 1 is 13. So spine 2. That's not going to be available until, hang on, let me delete these. Hilarious. All right, spine 1, 13. Oop, spine 2, 14. Oh, it's because I clicked the sort button. All right, so I made this much more difficult than it needed to be. Let me close this and open it back up again and not sort. Just leave it in this state. That way everything's in sequence. As soon as you click a sort button, it starts to reorganize things as you make selections. Oh, it's still doing it. Well, whatever. The borders are 11 and 12, and the servers are 15 and 16. Great. They all need to be in a deploy mode. And we'll update those assignments. Just one last quick scan. Okay. Great. We're ready to commit. We got green everywhere. See? Green, green. Lovely. Lots of stuff. We're going to hit commit. It's going to push configuration out to those switches. And while it does that, you're going to see all these anomalies until everything deploys and stabilizes. We'll go do DCB. Go to staged, physical, default on topology. Here, ASN spines. Make sure you're assigning the pools for data center B, DCB, loopback IPs for DCB. Oh, they're missing. Nope, they're not. Save. And over here, DCB loopback. And DCB fabric. Done. Interface maps. Edit. New. Only one option. Assign. Update. Here. Do the same. Check all. Only one option. Assign. Update. All right. Let's assign our devices. Our spines 23, 24. Oh, good. It's not doing that weird sorting thing anymore. Borders are 21 and 22. You go through this section as slow as you like. I'm doing it somewhat quickly because I've done it so many times. Make sure you set everything to deploy. You could actually add these, and if you forget to click deploy and commit, everything will look green like so. But fabric won't deploy. It'll model it, it just won't push the configurations out to devices. We'll hit commit here, and let's go check on the health of DCA, which seems to be having some problems. And there's a reason for that that I know about. That's why I created this funny slide here. It has a freaking out cat, and I'll show you what hasn't been done. We didn't tell any of the fabric devices what interfaces they're connected on. None of this. So if we go to staged and then physical and topology, and then we click on links right here and click on this cabling map, none of this information for these interfaces is correct. We have two options. We can go in here and we can manually change all this stuff, or we can rely on how awesome Apstra is. And we click this button here. What's going to happen is it's going to do an LLDP query, and it's going to figure out how everything's connected. It knows what your intent is, and it knows how the fabric is designed. It knows the relationship, at least the logical relationship between the leaves and the spines. It should be able to infer what those interfaces actually are. So we click that button, right? We click that right here. We say update cabling map. What pops up is the adjustments it wants to make. Really what you want to double check here is that it has the right number of links. It should be 8. If you see less than that, you might have a connectivity problem on one of your links. I talk about that in the first video in the series. Actually, maybe it's the second video under caveats, like if you have problems with links passing traffic. We don't have to go through and do this one by one. I'll just click update and it should be done. We'll finish that. Since we have updated the blueprint, we do need to commit this configuration again. So we'll hit commit, done. We'll go here and we'll see the same issue that we saw with DCA. As we discussed, we just have to update the cable map when we're done. This probe anomaly, I know what that is. We'll talk about it in the next video because I'm literally on the last slide creating this blueprint. Let's get back into DCB and wrap this up. Physical links, update the LLDP information. We see we have 8 links. That means that we likely have good communication. We'll see update the cable map, click update, click uncommitted. Wait for this to have stuff in it. Come on. You know, I've made changes. There we go. Hit commit. I'm going to pause and I'll come back to show you that everything is green. We'll talk about what the next video is going to be about. So hold on for just a second, please. You know, I said we were going to do this in the next video. I was wrong. I missed the step here. It's actually in this one. This is expected, this probe anomaly. We're going to make an adjustment to both data centers because I expect that DCB will show the same issue. It's a specific to virtual environment thing. Go into each blueprint, go to analytics, and then click on this probes button. You'll see we already have the anomaly there. We're just going to edit this and we're going to change this memory utilization threshold to be 95. This isn't an issue, it's just a behavior. We also don't have to commit that. The analytics sit on Apstra, so there's no commit to be run. And after a little while, all that stuff will clear out. We'll go here and do the same thing, because even though that error isn't up right now, it eventually will be. Update and done. I do talk about in the first video anomalies related to high CPU. There is a specific thing that triggers that. Actually, it's not, I keep saying the first video. It's the second video I put out in the series, but it's the caveats and considerations prerequisites video where I talk about the DHCPD process that needs to get bounced only once and then it's never a problem again. Quick edit, wouldn't you know it, I was just talking about the CPU utilization. Curse of wisdom here, I saw this and I'm so used to seeing anomalies related to memory, and I knew I'd forgotten to do the memory adjustment. I didn't even bother looking to see what this actually was. So I go into DCA and I look at anomalies. It is CPU. Look at that. So I can click on this and I can scroll down, and I can also get here just by going to DCA, analytics, probes. You'll see the issue. Click on this, and once you know it, sustained high CPU utilization. So we click on this, it'll tell us exactly which device. Border rack, leaf 2. We go here. I'm going to follow the same workflow I defined in video 2, the prerequisites and caveats. Show chassis routing engine to verify the problem. Sure enough, we're north of 1. Show system processes extensive. And there it is. Note the PID 14042. Request system process terminate 14042. Done. It will respawn that. It will never come back again. And I saw just a second ago that we look to have an anomaly in DCB. Who wants to bet that it is the same? And this time it's spine 2. Let's go to spine 2 in DCB. Show chassis routing engine. Yep, there it is. Show system processes extensive. Survey says DHCPD. Request system process terminate 14041. Done. We'll double check this one too. It's gone. Great. That's all you need to do. That problem will never come back. Hilarious. Awesome. I'd love the opportunity to actually show you that happening in real time. That does wrap this video up. The next video is going to be provisioning of tenants, routing instances, subnets, all that fun stuff. And then we're going to get into building our testing hosts. And then we get into the real fun stuff, which is DCI, getting connectivity out to the WAN, core networks. Good times, actually. So thanks for watching. Really appreciate you joining me. I really enjoy putting these videos together. If you have comments that are like, hey, this is great, or no, you do this differently, put them below. And if you want to actually have a discussion and download the materials and the collateral that I've created for the series, follow the link to the Juniper Elevate community thread for this video. And I will see you in the next one. Take care.